many qubits, which are two-level systems that we know how they work. We have some model for them, which is well characterized, that we can initialize into a quantum state of our choice at the beginning of a calculation, that have coherence, which means that we can keep their quantum properties throughout the entire computation, and finally are measurable, so we can read out our results at the end. We need to mix into these measurable, qubits, some set of controlled interactions that we can use to make them interact, which form a universal set of gates. So at IonQ, our approach is to start with a really good qubit. We use atomic ions, which store quantum information in actually the state of the outer electron spin compared to the nucleus. All that to say, it's a two-level system that's inside of this inherently quantum object. In our case, we're using a particular isotope of ytterbium, 171 ytterbium. And these ions are inherently identical based on the fact that they're ions that are coming from the same isotopic source. And they have long coherence times, and we can do near perfect measurements with them. The limit theoretically on paper for this particular ion is something like 4 nines, and there are ions out there that people have done even better measurement with. Another point that I want to make about these ions is that they are in and of themselves atomic clocks. Ions have been used in the atomic clock community for much longer than we've been doing quantum computing with trapped ions. As such, these long coherence times are not just a figment of our imagination. We know that these ions can actually, not our 171 ytterbium ions, but ones that are very similar to it in structure, can be used to actually define the second, or could be. The same transition that we're using in 171 ytterbium is analogous to the one that's used in the atomic clock. Also, these ions are electrically trapped in vacuum using electric fields. And this allows us to have very, very good isolation from the environment and allows us to operate at room temperature, unlike many other technologies. So for those in the room who are experts a little bit have seen this, what I'm talking about with the particular levels, this is the energy level diagram reduced of the ytterbium ion that we use. And our 2 qubit states are these 2 low-lying levels here that are separated by 12.6 gigahertz. The transitions between these sort of left-hand column and right-hand column levels are harder to drive. That's why I've depicted them with dashed lines. But the levels of interest are these 2, and then a couple of the levels in this excited state, which allow us to manipulate the ions with laser beams. So that gets me to the next point, which is the robust interactions that we have in the system. Our interactions are mediated by far-off resonant optical beams, which actually are at 355 nanometers, which is a really interesting wavelength because there are commercially available high-power lasers here where we can actually basically get as much power as we want, so as fast interactions as we want, by paying money to the same people who make the lasers for doing mask writing. These interactions look like driving microwaves in the transitions in the qubit for single qubit operations. By using 2 beams of light. And by changing around the frequencies of them a little bit, we can actually make a different kind of interaction between 2 different qubits using the same light by pushing the ions around using the same light. This state-dependent motion, the push that we give to the ions with the light, actually allows us to make our native 2 qubit gates. So in this recipe for a quantum computer that I was showing you before, there's one thing that I didn't talk about, which is how this scales. Because we know that right now we're in this era where we have very few ions. And I'm going to share today some results that we've been making with qubits that are in a chain of 11 qubits in our quantum computer. But as we add more, which we'll want to do to take advantage of the promise of doing computations that we can't do on classical hardware, there's a couple things that we have to think about. As this many of qubits goes up, the many number of gates and interactions that we need to do also goes up. Another way to say that is our computations are gate hungry. So the basic scaling is that if we increase the number of gates, interesting calculations start to look at things where we're using something like n squared entangling gates. And often, for many of the interesting applications, we're looking at n cubed or n to the fourth. And so this means that not only when we're scaling, we not only need to pay a lot of attention to how our qubits are scaling and the overhead that we're going to have for maintaining and keeping calibrated and working with those additional qubits, but also we need to worry about the fidelity of our gates. And the fidelity of our gates and our error budget actually per gate is going to go down, or we're going to need much better gates as we increase the number of qubits in our systems in order to do something interesting with them. So one thing that's interesting to and specific to many of the IonQ devices that isn't present everywhere else in the industry is that our connectivity in the system, the way that we make a single module for our quantum computing, reduces the overhead in these computations. And this is going to help us scale, because instead of needing swap gates to move information around a device with limited connectivity, we are able to connect all of the ions in a single module. So this full connectivity means that we're able to say, I want to do a 2-qubit gate between ion 1 and 11, or ion 1 and 5, and do that in one step. So what does this look like? This is a cartoon illustration of the microfabricated chip trap that we use to control our ions, with a chain of something like 20 ions on top of it. This is living inside of a vacuum chamber. To prepare the ions, we first have to get them. We load them from a neutral thermal oven source and ionize them using laser beams. Then we initialize the ions first by cooling them so that they're in their motional ground state, and then by using an additional laser beam to optically pump them so that they're hanging out in their zero state at the beginning of this computation. Doing our computations looks like turning on a series of laser beams, which physically from our control side is changing a bunch of microwave sources that control the acousto-optic modulators, which are just hardware devices that turn on and off and can modulate the intensity and the frequency to some degree of our laser beams. So when I'm showing you algorithms that we've executed on these machines in a few slides, what you should have in mind is a gate to us looks like turning on 3 laser beams, gate between 2 different ions. And a single qubit gate looks like turning on just 2. So those are those far detuned beams that I was mentioning earlier. In this case, they're directly making a microwave transition in the qubit. In the case of these 2-qubit gates, instead we're pushing the ions around, and the relative motion of the ions, depending on their state, is giving us a phase shift between the two, which we then can use to build up something that looks like a C0 gate, or that is a C0 gate. And so then we proceed through the rest of our computation in the same way until we get to the very end, and we want to do measurement. And to do that, we just turn on another laser beam. And when we do this, the qubits that are in their one state, one that we've identified as the bright state, glow, and we can collect some portion of the light using a high numerical aperture lens, putting this onto a set of photodiodes. And we can actually detect these ions very well. Our detection fidelity is something, or combined detection and preparation fidelity that we're realizing in these systems. Most of them are better than 3 nines. What I'll share with you is 99.5 about. So I've been talking about the demonstrated performance of the device. What are we doing? So in an 11 qubit setup, now for us, adding more qubits is actually very easy. We just turn on our oven for a little bit longer. We've actually been able to load over 150 ions into these devices, and we've been able to manipulate in some quantum way a few ions in a chain of about 75. But we've been able to do the most. We've worked the most with an 11 qubit setup. And so what I'm showing here on the nodes of this graph are color-coded our randomized benchmarking results for single qubit native gates on each of these ions. And so you can see the distribution of the single qubit fidelity across all 11 ions as it was when we were testing this device at that time here. And then the 2 qubit fidelity for every single one of the 55 different 2 qubit gates that we can make between different ions in this setup. These results, if you want to find them later, are summarized in our archive preprint that came out in March. So as I said, these single qubit fidelity numbers come from randomized benchmarking. The 2 qubit fidelity numbers actually come from us estimating from parity oscillations what fidelity the gates had to have. That is not a randomized benchmarking result. So to summarize, on average, we're seeing 99.5% single qubit gate fidelity in this set of data. We were seeing 97.5% 2 qubit gate fidelity and 99.3 state preparation measurement fidelity. This was coming from that same set of randomized benchmarking data that we took to get the single qubit gate measurements. Now, these measures of our gate performance themselves are not the way that we're going to push our computers forward, as these measures are extremely device dependent. If I were to measure what my single qubit gates and the 2 qubit gates look like, that's a different native gate than you would see in some other hardware implementation, and they have different overheads associated with them. So to actually promote growth in the industry as a whole, what we want to instead talk about is what it looks like if a user were to use our machine to run something interesting. And so what we did is we ran 2 example algorithms where you see some moderate expected change and expected speed up in the quantum version over a classical version approaching the same toy problem. And we ran this through our entire stack and looked at the results on the machine. So the first algorithm that we looked at was the Bernstein-Vazirani algorithm, which is a problem actually that says, okay, I'm given an oracle. I don't know what this function is. It's a function that looks like a product of an unknown bit string and the bit string that I provide. And we're asked to find the string that, this n-bit string that is encoded in the function. Classically, one way to do this would be you'd put a bit mask in each time and you'd read out the result, and that takes n queries. In the quantum world, you can do this with 1 query. Now, of course, since we know the result, we weren't going to put this through our full circuit optimizer, because then our full circuit optimizer would look something like flip the qubit that we know should be the one flipped and then read the result. That's not honest. What we did instead is we pretended that we didn't know what this oracle was. We optimized that by itself, and then we ran and measured what the output would be. And so what we found was that as we increased the number of 2 qubit gates, well, first I should say, we ran all of the 1,024 different implementations of the oracle for this problem. And we ran each of them with about 500 experiments so we could get statistics. And what we were able to see from that data was that on average, in 78% of the cases, we were able to, in a single shot, determine what the bit string was. And in just under 90% of the cases, the probability of success was better than 2/3, which is the BQP threshold, which is a threshold for understanding, for qualifying how well a device is performing relative to grading it in a quantum sense. So I've plotted here on your right the success probability that we saw as a function of 2 qubit gates. And you can see this is each of these points is basically the collection of oracles in which we had 0 to 10 different 2 qubit gates in the implementation. So of course for 0 and 10 there's only 1, there's no distribution. And the 2 tick marks on the ends of the bar indicate the max and min that we had in that full set. And then the inner box is the middle 50% of the data. So as we increase the number of 2-qubit gates on average, our success probability goes down. That's this. But this is in line with the fidelities that we're seeing, this kind of dashed orange line here. And there's an orange region here that's not showing up very well. That indicates kind of the measured, what we would expect to see from our previously measured results with kind of the way that our 2-qubit gates are performing. Now, we actually can learn more from our data than just seeing that the fidelities that we're measuring on our 2-qubit gates and our single-qubit gates give us something like the results that we're seeing. Because when we measure this, we don't only get whether or not we succeeded or failed, we actually also get the output state that each of the trials would have said that our oracle's hidden bit string was. And so this is what this looks like. On the left-hand side, you see the implementation of the oracle. So this is the encoded bit string. This I've converted, instead of writing it in binary, I'm writing it as an integer. And the output state is the same thing, but what I'm reading on the output of the device. And so the diagonal here is exactly the same thing that I just showed you in the last slide, except you can't really tell the variation within this top 10%, because I'm trying to show you the other aspects of the data, which are hidden in these like kind of 0.1% to 1% probability in our data set. And what we're able to see in the patterns of these off-diagonal bars are the effects of things that we're trying to correct in our devices, things like device crosstalk, things like our measurement not being perfect. But it turns out that these are actually very well described by a few simple models. And we're able, from a data set like this, to go back into our machine and say, okay, this is where our real issues are, and try to correct them. Now, we also ran one additional algorithm, another oracle implementation, oracle problem, the hidden shift algorithm. And this is a little bit more of a complicated problem for our computers to run because, well, if you look at the standard representation of one of the hidden shifts that you can encode in this problem, you'll notice that there's a lot of 2-qubit gates in it. In fact, in every single one of the oracles, we again ran all 1024 oracles, there are 10 2-qubit gates. And so this means that our success probability, we don't expect to be any better than our worst performance on any of the Bernstein-Vazirani algorithms, because we have more 2-qubit gates, which are our most noisy ones. And in addition, we actually have more single-qubit gates. And for this algorithm, we saw a 35% average success rate. And here, I guess I should say, I'm plotting this instead of against the success probability, instead of against the number of 2-qubit gates, which in this case is fixed, against the number of single-qubit gates in our optimized algorithm for the oracle. And the fact that these are mostly bunched and tight in terms of how there's no real dependence on single-qubit gate number just emphasizes the fact that we were seeing that our single-qubit gates are really good. And we, again, with this algorithm, can look at how our off-diagonal terms evolve. And here, very similar models with crosstalk and detection errors are able to explain the entire off-diagonal. I'm getting close to the end of my time. So I'd like to summarize by just saying what we've been able to see on this particular 11-qubit version of our IonQ system. In this system, which we benchmarked in the archive paper I was telling you about, we saw 99.3 preparation and measurement fidelity, 99.5 single-qubit gate fidelity, and on average 97% 2-qubit gate fidelity, which comes together to give us success probabilities that are sort of unprecedented on these 11-qubit devices for both the hidden shift and the Bernstein-Vazirani algorithms, which is super exciting. We're able to actually demonstrate this on these computers that really just a year ago we were talking about not having hardware and them being in designs. And In addition to the benchmarking algorithms that I've told you about, we've also recently put out results in the past few months on doing a totally different type of calculation on the same hardware. One really cool thing about the fact that all of the wires that we have in our quantum circuits are light is that we can actually operate these machines in totally different regimes with very little overhead. It's just us changing the way that we're programming the 2-qubit interactions. And so we use this to do a quantum chemistry simulation of the first 3 corrections to a simplistic model of water to calculate the energies in that. We've also demonstrated internally that we can use our cloud-controlled interface. And more recently, something I didn't put on this slide, we've actually shown some pretty exotic gates that are really exciting. These types of gates allow us to do not one 2-qubit gate at a time, but as many as we want from the full set of gates. So we could do a gate between these two ions and these 2 ions all at the same time if we wanted to in a single gate operation. So with that, I'd like to thank my colleagues at IonQ, to thank you for your attention, and I'll leave you with a picture of 2 of our machines taken about a week ago. Any questions?